I just want to go through this with you. You're going to see this over and over again, and the only reason I'm spending this much time on it is because it's so important. When you're going to be doing so many things, windowing will save you as far as getting rid of noise just out of band. And it's an easy way to do it. It's digital signal processing. As a matter of fact, in the actual radar class I had, one of the students built an entire radar, two of them actually, and they had problems with sidebands, and so they just implemented a simple Hamming window filter for it. So you'll be using this stuff in a lot of your classes. I assume at least if you do DSP, digital image processing, radar, probably a lot of the courses that have to do with Wi-Fi or telecommunications, things of that nature, you're going to be using this kind of stuff to get rid of out-of-band noise. Let me do it. I've got, this is 9.1, and I'm just going to show you what happens to a signal. That's with windowing. This is without. And this is a simple Hamming window. There's nothing here that's complicated in any way. It's a simple, just one simple Hamming window. And if you look at this in the spectral domain, this is fairly broad too right here. You can see all these side lobes over here just get wiped out by that Hamming window. And you can actually see the two signals right here. Now with radar, this signal right here that I'm showing, put my cursor over, you'd never see if you didn't do a window. You'd never know it's there. And a lot of that has to do with Doppler shift. So please understand, what I'm trying to show you with windows is something that you can appreciate and use later on. Remember what I'm telling you, and it's very simple to do. You take what, 0.54 minus 0.46 times cosine of 2 pi n divided by capital N. That's the number of samples, which is a trivial thing, and you're just multiplying that by the individual samples as they're coming in. All right, now that's the Hamming window. Some people are going to ask me in so many words, what are we responsible for on the test? I would never ask you to remember the Hamming window or something like that. If I asked you to, I would give you the Hamming or Bartlett's or any of the other windows. And if I asked you to do simply show me how you would multiply two functions to do that, I expect you to know how to do that, because if you've done this problem, it's evident. Everybody with me? All right, now, I gave you the solutions to this. There's a lot of ways to do this. It's simply two frequencies. He chose to do it in the book by putting the cosine, and the way he did it right here, he embedded the actual range from 0 to 99 right in there. So he basically put the range, the number of samples is 100 in there, and you didn't have to do it that way. You could break that out in a for loop or any other way you want, but you have to know how to do this, at least understand it. You got me on this? Understand? You notice right here, here he creates the F, that's the frequency value based on scaling. Remember, what you actually have is, when you have a sampled frequency, the actual frequency can be gotten or extracted from that. It has to be given though. And then what he has here is a simple FFT of this function x, and the FFT is a fast Fourier transform. It's the same thing as a DFT, only the number of samples is 2 to the n. This is the weighting function. This is going to be the window. It's a Hamming window, and he just multiplies that function, the weighting function, by the actual original function x, and he has it for 512. That's the actual length of the data window that he's going to present. And he has figure 1, and I put figure 2. I broke them out. He didn't, so you can see this. Now, this will be available to you. You don't have to do it that way. If you want to do it with a for loop or something else, do it. But you have to understand this basic thing. So if I ask a question about windowing, you can answer it this way, all right? Because I'm going to ask specifically something related to how you would multiply two functions to show me how a window would work on one, all right? And that's it with windowing. How many actually did this? If you did it, it should have been trivial. You just recreated what I put there. That's the only thing you have to do. Hamming window is the one that I use. There's one that will bring it down by 58 dB, the side lobes. Problem is the main beam is 3 times as wide as the original one.
You don't want that.
I mean, some people may, but I don't. Not for the work I do. So the main beam, you don't want that wide. That's it for this. If there are any questions, let me know. And I've got the second one too, but it's really, I don't think of any consequence to speak of. I can run it just to show you. I hope. Did it not run? Well, I'm not even worried about them. It did run earlier. Hmm? Oh, you know what? The license. It's got a FlexLM license. And the thing timed out. I'm not going to mess with this thing. I don't have a permanent copy, so it has a licensed server it has to go to. And I have to reestablish a connection all the time. And it's a bothersome thing. Okay, get your own copy of MATLAB. That's another thing. All right. So now, for the review. I said I'd take questions first if you had any. Get that screen up. If you don't, all right, I want to tell you one other thing. Test this. Can you shut off that camera? Just go up there and turn off the projector. Because it is comprehensive, it's not going to be, I'm not going to ask the, or I'm not going to have, there's no cables or anything. I'm not going to ask the level of depth that maybe you would get from a Lloyd Briggs, a Dr. Ridge or something, and have convolution or three functions or something. If you look at the past two tests, that's a good indication of the level of difficulty on the test coming up with the newer material. It's basically very similar to the homework, but you don't get tables, remember that. Except for, I'll give you some, if I ask you Hamming window or something difficult, you'll get it. But the basic stuff, remember, all the things we've done, you have maybe 4 or 5 functions that you know the pairings of, and from that on, you use properties to get all the other. And remember, Laplace and Fourier are identical virtually if the function is only non-zero values for t greater than or equal to 0. Then you can just take s and turn it into j omega. The big thing with the Fourier transform is duality, and that's true with the DTFT also. All right, so you kind of know that. Now, questions. I usually get several questions on the last day of class. Nothing. What?
Could you go over the system circuits using op amps a little bit?
Somebody just asked me this yesterday. Yeah, matter of fact, what he did was he gave me a specific problem, and he wanted to do a realization. This is a fair question, and finally there's usually something about this, so I'm going to go through this. I don't ask synthesis during the regular exams usually, but let me go through this one. You want to give me the exact one you do? Not you, the guy next to you. He has this. We're going to use op amps to do this. Matter of fact, we're going to have some fun with this. We're going to not just do this, we're going to do this with a digital filter as well. Go ahead.
3s squared plus 4s plus 5. All over s squared plus 6s plus 7.
Now, I want to tell you that's a standard transfer function. 2 polynomials, second order on top, second order on the bottom. Very easy to understand what that is. If you want to see what it looked like, you could plot it. I'm not really, if you look at this in the limit at high frequencies, if you look at the power of s squared top and bottom, in the limit this thing will go to 3 at very high frequencies. It'll have a gain of 3. In the limit at low frequency, when you're at s equals 0, it's 5/7 is the gain. In the middle, you're not sure. It's got a couple of bumps, basically. Follow me on this, class? But this is nevertheless a filter, a transfer function that you have to realize a circuit that'll do. The way we always do it, first we break it into 2 functions. The first will be the top, 3s squared, plus 4s, plus 5. Then it's going to be times 1 over the second, which is s squared plus 6s plus 7. Now I did it for a reason that way, and I'll explain this. We're going to go ahead and realize this is going to look like 2 transfer functions. I'll call this h1 of s and this h2 of s. All right, that's my h2 of s here. Here's my h1 of s. Is everybody with me on this? Keep watching. It's a simple realization. We're going to realize h1 of s first. And we're going to do it with block diagrams first, all right? Before we do op-amps. The block diagrams, this one is going to take this signal, input signal, which I'll just call x of t. You can call it x of s if you like. doesn't really matter. Now after that, we see we've got a multiplier. Oh, well, I'm sorry. Then we're going to divide top and bottom by s squared. I didn't say that yet. So we're going to divide that term and this term by s squared. So let me put down what it actually looks like. This would be equal to 3 plus 4 over s plus 5 over s squared times 1 over, and then it's going to be just 1 plus 6 over s plus 7 over s squared. And this first one right here is my h1 of s, and this second one is h2 of s. All right, now to realize the first one, h1 of s, and this should make sense to you. Remember, this we're going to multiply by the input, right, to get the output. Everybody follow me on this? Think of the s domain, x of s. Comes in there, right off the bat I see a 3. So I put a 3 here, it's a block. It just means it's going to amplify that first part by 3, right here. With me? Now I need a 1 over s. So I come down here, and I have a 1 over s block. That's the flow of the signal. And then that has to be multiplied by 4. We know we're going to add these together in a second. Does everybody see what I'm doing? Can you all see it in the back, far back? Next, I'm going to go ahead and I need another 1 over s block, right? And then I take that and multiply it by 5. Now, I need to take all these and add them together, correct? For a summer. So I can just, the symbol for a summer is just this. And these, you're normally going to put, whether it's a positive or negative subtractive effect, and put one more plus here with an arrow. So that takes care of that part of the circuit, that part of h1 of s. It's still a block diagram. But you all see what I'm doing, right? Now this part is the part that requires an understanding of what I call negative feedback. So I'm going to block that up here to show you a block diagram. Remember before I said that if you had a forward gain of A, and here it's negative feedback, so this is the input, but this is going to be a plus, this is going to be a minus, and you had a reverse feedback of beta or B, and this was the output, right? Y of S, and this is the input X of S. Well, the H of S for that circuit, some of you remember that, which is Y of S over X of S, is just equal to A over 1 plus AB. Y'all remember that, class? Give me a show of hands, how many of you remember that? This almost guaranteed on the final. You're going to see stuff like this. All right, now here, remember A is the block right there, B is the block right there, right? You'll notice the key thing is that 1 right there. All right, so I come over here, and luckily I didn't have to modify this at all. There's a 1 right off the bat when I divide by s squared. Follow me? So what I can see is the A is 1 here. You all see that? So when I come over here, I can just have the forward gain is 1. I have nothing to worry about. It's basically the block is just 1 if you want to put a block in there. Y'all with me? Now what happens? This is what?
That's E.
Isn't it, class? Y'all see that? That's going to be the negative feedback going back here. So this is the plus. This is the summer right there, and that's negative. Now the first term is a 6 over s, right? So now I come from here and I bring a 1 over s block, right? And then I take the output of that and feed it back through a 6, right? The value 6, and then that comes back, it's a negative feedback. Then I need another 1 over s block, right? And that has to be weighed by a 7 here, and that comes back in negative feedback. And now, you don't even need that part that I put here, by the way. That's a straight line. I just put the 1 in to show you. That is the forward gain in this case. Are you with me, class? All right, now, in a block diagram sense, I realized that transfer function, didn't I?
Yes.
All right, now, the next thing we talk about is how would you realize each one of these steps? That step right here, the summers, we've gone through this, I don't know if you remember it. And so I'm gonna do this. Does anybody have any questions of what I've done right there with the 2 stages? How many understand this right here? All right, now to realize this, and yes, sir.
Could you combine the summers too?
Well, I'm going to tell you, the reason I wouldn't advise anything like that is because usually this is done as distinct stages, and when you're talking about feedback here, there's a timing involved. I can't get into this when you're talking about higher frequencies especially. This circuit, this thing has a timing involved too in it, and I'm not going to, I'm very careful to say you can't, but I would not advise it. That's my opinion. Now, the op amps usually, remember, we're going to do this, why don't I do the summer right now? And you'll see what I'm up to and why I'm concerned. Go for it. So I'll do it right here. One other thing too, the reverse of what we're doing, oh yes, sir.
I just want to make sure I understand the concept. So like, when it goes straight down, that's when you're using the variables and like.
Well, this is just a 1 over S term, right?
Right.
And see, I'm trying to realize this function right over here, right? And I showed you the block diagram, A and beta, right? The negative. So here's the summer that takes the negative values, right? And then over here, what I need to get is a 1 over S for starters. Then I have to multiply by 6 that value. And then another 1 over S is a 1 over S squared, effectively, right? So this, when it's coming out of here, it's 1 over S squared, and I have to multiply it by 7, but it has to be fed back in a negative way. That's the reason.
Same thing on the other side, except the top is amplified by 3.
Yeah, and I mean, here we don't do, yeah, exactly. There's no negative feedback. It's just straight addition, right? You're taking the value 3 times that, then 1 over S times 4, add it, and then 1 over S times 5, add it together. All right, now about the summers, just to make sure. And I'm going to say one thing. You can probably look and find a whole bunch of designs on summers in general. The one I'm showing you is the most basic and most common one. That's the reason I'm going with it. So for a summer circuit, the simple operational and ideal op-amp summer circuit is this one. This is a summer. Simply, you're going to have 3 resistive values. Here, I'm just going to call them all R. There's no difference. Tie those together. All right. Those are going to go to the negative terminal of the op-amp, ground the positive. Another value R here. Then you're going to have what's really just, it's something that's an inverter. That would be the output. And here, V1, V2, V3, and you can have as many as these as you want, right? All the voltages are with respect to ground, understand that. The output right here, how many remember doing this summer right here? All right, it's a straightforward thing, right? If you got V1 here, right? Well, the voltage here is ground, that means the voltage here is ground, right? It means the current through here is V1 divided by R is the current through here, right? The voltage developed across here would be V1 over R times R, it's plus the minus, so the output would be minus V1. This is a simple inverter, we get V1 if you just have V1 there. If I have V1 and V2, it's still grounded right here, so now I have a current V2 over R added to that first current, right? Means the voltage here would go up by V2 over R times R, right, or really just V2, but it would be a minus as well, add to that, and this would invert it. So the final bottom line is this V out right here would just be V1 plus V2 plus V3. Now, we could keep going on and on, couldn't we? Let me finish my thought here. Do you all agree with that? We could add 30 of these. However, there is a limit on how many you can do. And the reason is there's no such thing as actually an ideal op-amp. There's a slight offset current here. So you have to be aware of this. This works in the ideal state perfectly. But you start adding up hundreds of these things, there is a slight offset current. Now you cause the output right here to float up and down, depending on what the offset current is, and that's what you're going to learn about in your analog design class. I don't think you've had that yet, right? It's coming up, but you'll learn about that. And there's ways to tune that out and deal with that, but I'm talking only ideals. For simple cases, this works perfect. Yes?
Would you be able to build like a 1 over S term into your summer by replacing that R with a
Yes, but you're not, now see here, we're getting to a point where we don't want to make it too crazy. Yes, he's saying, why not put a capacitor right here so we can get a simple pole? Yes, you can do that if you want, but I prefer not to break it. I don't want to try to make this too complicated. You're absolutely right, you could do it that way. As a matter of fact, you could put an RC network out there so that you could actually get a first order pole and you could adjust that. Yeah, but you're getting ahead of the game. We don't need to make it that complicated. That's a simple summer. Where does that go? Here and here. Only this one's negative. Follow me? So this one you wouldn't even need this part right here. Everybody see this class? You just keep that in mind. Next. That's the summer. Now, for this 1 over S part, which you just got onto me about. You know, some of you see through this, you can see ways to make it much simpler. You're absolutely right. But right now, maybe simpler for you, more complicated for others. I'm just trying to give you the basic design concepts. Next, suppose we have just this. This is a simple, it's really called an integrator. So this is my input and this is my output, right? The impedance of this is 1 over SC, right? Now this is the one in the last test. A lot of people memorized the formula and you forgot about the fundamental way an op-amp works. Remember, the way an operational amplifier always works is there's no voltage difference between these terminals and no current into it. Remember that. So if you get a question with an op-amp where you have to do analysis, always remember that. Don't default to formulas. All right? Be careful about that. But for this one, I can make this case, since this is ground right here, that's ground to 0 volts. This current is V1 over R. It's as obvious as it looks. Do you agree with me?
Yes.
If that's the current there, I'll call it I. That's the current here because no current flows into the negative terminal. There is a very slight current, but it's so slight we don't worry about it with this simple design. You're going to see in more complicated cases you have to worry about it, but that's later. That's the second order design stuff that you'll learn about. All that current flows here. It means it develops a voltage here that's equal to this I, or V1 over R, right, or VI times 1 over SC, correct? Right? It also means that the voltage output here is minus that, because this is ground and this is a voltage drop. It's plus to minus that value. Do you agree, everyone? So that voltage output is minus V1 over S times RC. Or I have V out over V1 equal the transfer function H of S of the circuit, or it's really minus 1 over SRC. Now if I make RC equal to 1, it's minus 1 over S. Is it not, class? That's making RC 1. I'm just showing you a simple block for the 1 over S. Agreed, everyone? With that, I can just take this into a circuit with R, that's an inverter, and now I have 1 over S as my transfer function for this circuit, input to output, from here to there. Do you all agree with me? All right, now that seems like an extra you're going to put too many op-amps and stuff. In a sense, you are absolutely right. There's a minimization process you're going to learn about probably. There's all sorts of stuff. But for now, this is a simple way to implement a 1 over S function. You all with me on this, class? Now, if you wanted gain, if you wanted not 1 over S, but like in those terms, if you wanted minus 6 over S, there's no quiz today. But our final exam is, what is it? Tuesday at noon, all right? Be here Tuesday at noon. Put it in your calendar. Thank you. But some of you are saying, well, suppose you wanted 6 over S. Well, guess what? Then 1 over RC would be 6. And you can eliminate a step. You all see this? I'm just showing you a simple way to do it, and it always works. This will always get you the 1 over s. It's consistent with his book. Now, then the last thing is these simple blocks where you have, remember that Jay had 3 times something or 4 times something, right? Here, I'll do it right here. This is, and I'm doing it in the most simple way possible. There's other ways to do this, but in my opinion, it's the simplest. If you're going to implement that, if I want just a simple gain, call this R1, that's R2. Coming out, that's grounded, that's the negative terminal, that's positive terminal, here's Vn. At this point right here, my V out is equal to minus R2 over R1 V in. That's what it is at that point. We can prove that, but how many understand this? So now the ratio of R1 over R2 is talking about the proportional gain here. I know it's a negative sign. If you get rid of the negative sign, just put an inverter. The simpler R here, negative, positive, grounded, another R here, and now my output over input for this circuit would just be R2 over R1, and you can make that 3, 5, 11, 100, whatever you want. Understand that? That's a simple way to get a gain block, a solid value. So now you've done summers, you have the 1 over S, and there's the simple gain blocks, and that's what makes up that. Now, some of you are thinking, well, what could you possibly ask me? I could ask you to do a block diagram representation, the way I just showed you, and maybe implement a part of it, something like that. But you all follow me on this one, class? It's not that difficult, but you have to know what you're doing. And remember with operational amplifiers, with analysis, no voltage across the inputs, no current into it. That's the way you analyze it. You don't try to memorize a bunch of formulas or inverter, differentiator, all that stuff. Yeah.
So you probably would ask us to try and implement something like that block diagram you just drew a couple minutes ago with op amps. You wouldn't ask us something that
Something
size.
like that. I may put the blocks together for you and ask for values.
Okay.
Because there's limits to creativity. And a whole bunch of extraneous stuff. I can only imagine some of it. Every time you do design, when you ask a question for design something, you open up Pandora's box of everything you can imagine. And sometimes the students are right. You just never see that one coming. All right. So that's that. Anything else? Any questions? It's a good question, actually. It's been a while since we've done that. Well, you know about duality, right? So, whether you love it or hate it, you're going to see it. So get used to it. Duality is something we covered a fair amount. That's coming up. Some version of duality. Something we haven't done a lot of in a while is probably, well, we could do some convolution. We haven't done any discrete convolution in a while. That's part of, Z transform stuff is fundamentally, if you have an X of n convolved with an H of n, that's convolution, right? It's discrete convolution. The way to do it is with Z transforms, but an actual discrete convolution problem usually involves summing something that has those exponential terms where you get geometric series. Y'all remember this stuff? So off the bat, let's make sure we know this. This is one thing. If you have a summation in general from n equals, and I'm going to put Q1 to Q2 here. I'm not going to prove it. And I have any value a to the n. A can be anything. It can be complex. A could be like 1 plus J2, or it could be 3 at an angle of 40 degrees. It can be anything. There is no limit to what A can be. You understand that? It is not just real. Well, if I have this, that's actually equal to A to the lower value, Q1, minus A to the upper value, plus 1, Q2 plus 1 over 1 minus A. We could prove that if we want. That's the most general way to write it. Y'all remember this?
Yeah.
Now, usually, it starts at 0, almost always. Makes this one simply 1, usually. And if it's an infinite sum, then this one always goes away. Or else you have something that's undefined because it's going to blow up. It'll be too large. Follow me, class? So usually the way this ends up, not always though, and it's usually for n equals 0 to infinity of A to the n is simply equal to 1 over right? 1 minus a. You all remember that? And that was the basis for a lot of Z-transform stuff, this right here. So for discrete convolution, at least, suppose I give you a simple discrete convolution problem. We could do it with either finite or infinite infinite domain functions or infinite numbered functions. If I have x of n here equal to 1/2 to the n u of n here, and I would convolve that with, say, let's convolve it with h of n equals u of n minus u of n minus 3. Are you with me? Now, I showed you the way I like to do them. I like to actually draw these things out like you do with continuous time. And find the one that changes the most. Don't flip and shift it, right? And by the way, for the convolution of these two, call it y of n. The symbol is x of n convolved with h of n. And that's actually equal to the sum, right? Here it's n equals 0 to infinity, or not n, I, pardon me. I equals 0 to infinity. I'm going to leave this one alone. I'm not going to flip and shift it. It would be x of I times h of n minus I. That would be the definition of convolution. Remember, I chose to leave the x alone because it's got an exponential decay. The other one is a block moving through it. Understand? So I'm going to draw it up first, then we're going to write it down in terms of the sum. I want to make sure everybody's on me here. Can you see it in the back? All right, got to make sure you can read my writing. All right. So for this one, well, what does that look like? It's exponentially decaying, right? What I can do is actually do this. We know this is values of n here. I. And it's going to be really something that has an envelope like this. And really it's discrete values. First value would be 1, then 1/2. Well, it doesn't look like a half, but it'd be 1/2, and so forth. It keeps going down and down and down. So it's just all those values. Now the next one, the one I'm going to flip and shift, right, is this one. Well, what does that really look like? If I just drew it here, if this is versus I, and I have u of I minus u of I minus 3. Well, think about this. When I is 0, this is 1, right? I is 2, this is 1, this is not on. I is 1, that's not on. I is 2, this one is still not on, right? When I is 3, it goes to 0, 0 from then on. So it looks like this, basically. And you can see the envelope there. It looks like a pulse function, right? That's all it is. You all see it? Now take that, flip and shift it. Well, first, when I flip it, it goes around the axis, right? So now it looks like this. I'm going to start at 0, n equals 0. And this would be, if this right here is h of n, this is h of minus I right here. Y'all agree with me there? That's h of minus I, correct? I simply flip that thing, right? I've inverted it. And I've replaced n with I. Next, this is for I, by the way, what I'm showing you there is for n equals what, class? 0, correct? Now think about it. If it's 1, it does this. Right? That would be 1 minus I. Agreed? If n was 1. Can everybody see this, class? Normally it's n here. I'm showing you a specific value, right? When n is 2, it's this. You all see that? 0, 1, 2. When n is 3, what happens? It's that, and that's 0. Can you all see what's going on? So I'm going to go back, and I'm going to say, start here, that's n0. Well, between 0 and 2, I'm only going to be summing from 0 upwards, right? So I can say now my y of n, let me do it over here. I can say my y of n is equal to simply the summation of 1/2 to the n from, 1/2 to the I, pardon me, from I equals 0 to n, for n greater than or equal to 0, less than or equal to 2. That would be the value. We can sum that in a second. You all agree with that, class? Right? I've only done the sum and I'm limiting the limit right there, but it's still I right there. So at 0, it's 1, right? At 1, it's 1 plus 1/2, or 3/2, right? At 2, it's 1 plus 1/2 plus 1/4, right? You all see what I'm doing here? Right? Now that's as far as it goes. So you got 3 values. Do you follow me on this? Now what about when it's greater, all of a sudden when it's greater than 2? Take a look at what it looks like. Now it's greater than 2, right? I got this. So this is going to be n, right? N's 3 there, correct? This is n minus 1, n minus 2, correct? You all see what the sum is now? n greater than 2, what is it going to be? It's going to start at n minus 2 and go to n. Follow me? I will go from n minus 2 to n, right? You all see this? And it's just going to be 1/2 times that. So then you could say y then will be equal to the summation from I equals, and then in this case it's n minus 2 to n of 1/2 right here to the I. And you could write that out as you can just do this if you want. What is this going to be? This is actually what? 1/2 to the lower value, n minus 2, minus 1/2 to the upper value plus 1. So it's n plus 1 over 1 minus 1/2. And you can fuss with that all you want, but that's the right answer. You all see what I've done there? Now that has an exact parallel to the way you would do this if it was continuous time. Why don't we do it continuous time? Because it's been a while. All right? I'm going to do the same problem continuous time. I don't think I've ever asked you to do this one in a quiz or anything. So for continuous time, and I'm going to say this too, this has always been my opinion that convolution is the most difficult of the concepts that we cover. Okay? It's my opinion, and you can ask your friends. You get something called correlation later. It's very similar to convolution. Both of those two are complicated. So now I'm going to convolve 2 signals. I'm going to say my x of t is equal to, I'll just call it e to the minus 5t u of t. And I'm going to say my h of t is equal to, and this one I'm going to say it's u of t minus u of t minus 3. You can make minus a if you like. I put a 3 in there because it'll make the answers a little easier. All right, so how do you do this one? I'm asking you. Which one aren't we going to flip? The x of t, because it's the king, right? So now I come up here and I simply put down x of t, which is e to the minus 5 tau time, and like that, and it's for tau greater than 0. It doesn't matter if you use tau or lambda. It's a dummy variable, right? And now we take the second one and we flip it first, right? So this by itself, if I just plot it versus t, it looks like this. 1 out to 3 goes to 0, and it's 0 forevermore. That's versus t. Do you all agree with me? Can you all see this, by the way? Now I flip it, right? I get rid of t, put lambda, or minus lambda actually, and I move it. So now I have this. This is going to be my t, and this is going to be t minus 3 here. The height of this one is 1, right? Now for t less than 0, there's no overlap. Do you all agree with that? Can you all see that, people? You're going to get a convolution problem, so just work with me here. All right, now between t equals what? 0 to 3, right? I can say my output, y of t, is really going to be the multiplicative. These two multiplied together and the result integrated, right? Well, this is 1. I like that value, and I don't try to make it too tough. 1, 2, 3, something like that. Something where it's really easy to multiply. I'm not going to do something and have this you know, I'm not going to do this to you, I'm not going to give this a staircase, you know, where you go nuts trying to figure out the different ranges. I don't want to have you go nuts, but I'm going to make sure you know how to do the basic things. I mean, I could make it a ramp, something that's a definitive functional form, like a minus t or something like that, or a t. All right, for this one, it's just going to be the integral of e to the minus 5 tau d tau from 0 to t, and that's t greater than or equal to 0, less than or equal to 3. Do you all agree with me there? Okay.
Uh-huh.
I'm making sure I see everybody's eyes here. Do you understand what I'm saying? All right, now what happens when y of t for t greater than 3?
The bottom of it changes to t minus 3.
Did you, whoever, I hope you all heard him, he's right. The thing that changes the lower limit, right? Now it's still going to go to t, right? The window here always is going to have the t as the leading edge. But now the back end changes. Now we have this. Now we're going to have t out here, t minus 3 here, still the height of 1, and here's the overlapped area, right? So it's really 1 times this, where it's really this integrated between here and here. Follow me? I know a lot of you see this, you think you see this, but until you do some of these problems, don't trust yourself. People make mistakes on this like you cannot imagine all the time. And I gotta say one other, what? I'm sorry, we asked a question. If you're making a comment, it's fine, but you got a question, make sure I hear it. Here, over here, this is still going to be the same kernel of integration, e to the minus 5 tau d tau, but now the lower limit goes to t minus 3, upper limit goes to t, and that's it. Make sure you know how to do integrations. Something else I'm going to tell you that people got stung on in the first test. The problem I gave you was something like this. U of t minus 1 minus u of t minus 3. Now that doesn't start at 0, it's got an offshoot, right? So when you flip it, it doesn't land at 0, there's no overlap. It has to move for 1 second. Do y'all remember this? Things like that are possible too, so make sure you're on your game, you're sharp, you understand how to do those kind of things. I've got about another 2 minutes. Does anybody have a specific question? Now, yes?
Well, just so in that case, you would just, the lower limit would be 1 to t?
Let me do it. Let's do this one right here. Because I think this is a fairly easy one to see. First, just take this, and now I'm going to put down, just so everybody sees it, this is going to be my h of minus tau with no change. It would look like this. This would be minus 1, this would be minus 3, and height of 1, right?
Mm-hmm.
Now, when you start moving it, what you're doing is adding t right here to that argument, or t here, or t here. Follow me? Now, please watch this. I didn't do this well one time in class, so I want to make sure you see. The upper limit is t minus 1, right? It doesn't cross over to this area where it will overlap the other function until t is greater than 1. Do y'all see this? But the first part of the overlap, the integration would be from 0 to t minus 1, right? And that would be true all the way up to what? 4 seconds, isn't that right? Because the back end here doesn't go through there until you're t greater than 4, right? Or, hold it. Yeah, that's right. Are you with me? Until it moves all the way through. And then you would have 2 different top and bottom limits after that point. Please make sure you can see this one and do this one. One other point I'm going to make with Laplace and Laplace transforms in realization. Remember to do partial fractions correctly. Remember, if you're going to do an inverse Laplace transform, partial fractions, doing that is, we haven't done those in a while either, so make sure you know how to do them. Now I'm over. You know what I'm talking about. If you have something you can factor, right? S, let's say you have something a over s, and then you have an s squared plus 3s plus 2, something like this. You know that factors into s plus 1, s plus 2, times s downstairs, and each one of those is a pole, and you have to calculate the values. All right, I think you know what I'm talking about. If you have questions, somebody's going to ask me when you're in your office. All right, on Monday, since our test is Tuesday, right? I'll be in Monday afternoon. I'll probably be in there I'm gonna probably, at least from 1 to 2, 1 to 2, unless I get called out. If I do, I'll send a message to everybody that there's a meeting cropped up. But if you need to see me more, just send me a message. All right? See you.
Okay, thank you.